My name is Jahidul Islam. I am a student of Electronic Engineering Department of Kaungun University. Now I will discuss on review of MMIC technology, and this is first chapter of Introduction to MMIC Technology book. The MMIC means the monolithic microwave integrated circuit, and the word monolithic is derived from the Greek letter monos, that means single, and lithos, that means stone. Thus, a monolithic integrated circuit is built on a single crystal. Monolithic microwave structures or circuits, MMIC, are a type of integrated circuit or device that operates at microwave frequency range. Moreover, these MMIC circuits are introduced into the same semiconductor substance with combining fabricated active and passive components together. Now, the monolithic microwave integrated circuits are widely used in communication, radar, bio, and RF sensing systems. Radio frequency ranges from 3 to 3 kHz to and 300 GHz, but the MMIC circuit only operate at microwave frequency range. Different assigned frequency range for different purposes are table 1.1 and 1.2. In applications of frequency range in table 1, we can see 3 to 30 kHz, very low frequency. It's a millimeter wave, and application in marine communication. 30 to 300 kHz, low frequency, kilometer wave, is application in wireless station. 300 to 3000 kHz, medium frequency, hectometer wave, its application in ASF communication. 300 to 30 MHz, high frequency, decameter wave, its application in amateur radio, that means ham. 30 to 900 MHz, very high frequency, meter wave, FM and TV and beeper. 300 to 3000 MHz, ultra high frequency, decimeter wave, its application in mobile. 3 to 30 GHz, super high frequency, centimeter wave, satellite communication. 30 to 300 GHz, extremely high frequency, millimeter wave, space communication. Finally, 300 to 3000 GHz, decimeter wave, its application in electric wave and astronomy. There are also some frequency range for specific application in table 1.2, cellular, and its frequency range for transmitting 824 to 849 MHz, for receiving 869 to 894 MHz. There also have another application, GSM, global system for mobile communication. It's have different frequency range for transmit and receiver. For personal communication system, PCS, it's have different frequency range for transmit and receiver. And the wide local area network, WLAN, it's have several frequency ranges in megahertz. And direct broadcast satellite, it has one frequency range in megahertz, and local multi-point distribution system, it has only frequency 28 GHz. And ISM, industrial science and medical, it has three different frequency ranges in megahertz. Now I will discuss on history of MMIC. The origin of MMIC is 1964 at a Texas Instrument government-sponsored program. MMIC technology shares a common root with silicon monolithic and digital IC technology because silicon MMIC switches, mixers, IF amplifiers, phase shifters, all were developed at Texas Instruments in late 1960. Then the Pengelly and Turner used MESFET devices on gallium arsenide to fabricate an X-band 10 GHz amplifier in 1976. Since 1988, DARPA, now ARPA, has conducted extensive research and development under the MMIC program. The study resulted in commercial applications such as DBS TV receivers and AC-air wireless LAN networks and personal and cellular communication. Now I will discuss on comparison between MMIC and hybrid MIC. The table depends on merits of MMIC and hybrid MIC. In the case of MMIC, non-returning engineering NRE is cost is very high, but on the other case, NRE cost is very low in case of hybrid one. In case of the MMIC, the size and weight are very small, but in case of the hybrid MIC, the size and weight are very large. The mass production cost is very low, but the hybrid one, the mass production cost is very high. The MMIC have a very good design flexibility, but hybrid one also good, but not good like the MMIC. The MMIC have relatively good broadband performance, but hybrid one have a limitation in case of broadband performance. And high level of integration is possible in case of MMIC, but in case of the hybrid one, high level integration is impossible. In case of the MMIC, the reproducibility and reliability are excellent, but in case of hybrid one, the reproducibility and reliability is just fair enough. The advantages and disadvantages of MMIC and hybrid MMIC. In case of MMIC, the main advantages is the mass production cost is low but requires significant investment to develop. The disadvantages are the state-of-the-art performance is not possible in case of MMIC. Complex MMIC have poor yield due to multi-capacitive effect. Hybrid MMIC have several advantages. The first one is cost is very low for simple circuits and requires a comparatively small investment to develop. And the size can be small due to compact multilayer substrates and with passive components. Can choose the best transistor possible from a range of manufacturing companies, and time required for layout construction test is comparatively small. Disadvantages does not have good reproducibility and reliability due to hand tuning and bonding of devices or components together. The application field of MMIC. MMIC main application field in military, space and civil. In case of military applications such as smart mutation and decoys, electronic warfare, remote sensing and altimeters, passive MMW, imaging and instrumentation and so on. Space field include the applications such as satellite TV receiver, satellite for communication, radiometers and astronomical fields, synthetic aperture radar and so on. In case of civil field, there are several applications such as satellite TV receiver, BSAT, wireless communication, fiber optical system, LANs, GPS, Bluetooth and high-speed internet. The major foundries of MMIC. On the base of the 3,2,5 compound such as gallium arsenide, gallium nitrate, including there are several major main fabrication companies. For example, Samsung, UMS, Analog Device, Atmel, Consextant, Harris, IBM, and etc. companies for 3,2,5 compound gallium arsenide and gallium nitrate. And the basis of the silicon, there are several companies: National Semiconductor, NEC, Philips, Qualcomm, RF Micro Devices, and also another companies and IBM companies based on both the silicon and 3,5 compound gallium arsenide and silicon carbide. They actually main fabrication companies are the Raytheon and Cree Inc. These two are very popular for on the base of the silicon carbide process. Several materials used in MMIC. Some common materials used in MMIC such as the gallium arsenide, indium phosphide, and aluminum gallium arsenide, and also including silicon carbide, silicon germanium. And the properties are based of common properties: electron mobility, resistivity, permittivity, thermal conductivity, wafer size, wafer cost, energy band gap. We make a table on some materials: silicon, gallium arsenide, germanium, silicon carbide, gallium nitride. We can see electron mobility of silicon, uh, 15, 150, and on the other cases for germanium, gallium arsenide are very high electron mobility. And in case of gallium nitride, in a second position in case of the electron mobility. In case of the resistivity, the silicon 103, but in gallium arsenide 108 in resistivity. And permittivity, all properties are important for materials used in MMIC because these properties are key factors the depends for the performance of the MMIC circuit. Now I will discuss on active devices of MMIC, and gallium arsenide MOSFET is active devices of MMIC. We can see some three figures, and first figure for cross section of the MOSFET with a superimposed lumped component equivalent circuit for MOSFET, and second one a basic schematic of gallium arsenide MOSFET cross-sectional view it is a, and another last one is equivalent circuit of MOSFET. And there are some parameters: CGS, capacitance between the source and the gate; IDS, the gain of the device; RDS, the resistance of the active channel layer; CDS, the capacitance between the drain and the source. Gallium arsenide HEMT, gallium arsenide high electromobility transistor, is another active device for MMIC, and this device is the passive structure bandgap characteristics as with the comparison of HEMT and PHMT we can see in three figures. In case of the PHMT, there is a extra layer near to the substrate, gallium arsenide substrate, we can see from the figure. Another active device, 3 to 5 compound HBT, is actually modified version of bipolar junction transistor with a wide bandgap emitter and narrow bandgap base region. A schematic cross section is figured out in the below figure. There is a two figure. Figure 1 is a cross sectional view HBT9, and figure 2 is equivalent circuit of the device. Silicon germanium HBT. Silicon and germanium have diamond lattice structure, and the lattice constant of germanium is 4% greater than the silicon lattice constant. The emitter has a wider band gap than in the base. Although the silicon germanium has lower band gap with different lattice constants, its electron mobility is approximately 2 times faster than that of the silicon. And in figure we can see a schematic diagram, band diagram, and ACM photomicrogram অর্থাৎ ACM image of first generation silicon germanium HBT. We can see collector and base is the middle in case of the silicon germanium HBT, and there is a 2 and 2 P plus, that means P type, and in the middle one is polysilicon N type. Another one is silicon BZT. High performance silicon BZT can fabricated with uh, FT up to 25 GHz. The typical features of such devices include emitter points of 0.4 micrometer, the double poly self-aligned technique, and side wall spacer technique, buried layers, and selective collectors. schematic diagram of high performance silicon PCT we can see in the figure. And the oxide layer, there is a collector, base emitter, and N plus polysilicon, P plus polysilicon implanted collector, N plus bridge layer, and substrate is a P-type substrate. Now I'll discuss on passive devices of MMIC. Inductor. MMIC inductors can be realized using straight, narrow tracks, ribbon inductors, single loop inductors, or multi-turn spiral inductor. Considering microstrip ribbon inductor with its equivalent circuit, as shown in the figure 1.9, its inductance, shunt, and capacitance can be calculated using the following equations. Z are common for abbreviation for impedance. F is the frequency, AC is the capacitance, L is the inductance, and the microstrip ribbon inductor. There is a microstrip layout and figure B equivalent circuit. The choice of inductor is depend on the required inductance and its implementation in the circuit. Another common passive components are capacitor and the MIM capacitor, which has high capacitance per unit area, and the interdigital capacitor can be used in MMICs. This capacitor is composed of two metal plates separated by a dielectric material. The choice of capacitor depends upon the required capacitance value. MIM capacitor, figure C, and figure A overlay capacitor, figure T equivalent circuit, and B is the interdigital capacitor diagram. Another important passive devices component resistors. Resistors are used for feedback circuits and setting the bias point of active devices, isolation, terminations in power combiners and couplers. Two types of resistor are used in MMIC fabrication, including thin flames of lossy metals, light lit up gallium arsenide active layers. Figure shows schematic of each of these two types of resistors. The resistance for both resistors is given by R, PS, LA, and A is equal to W multiply T. T is the thickness, W is the width, and PS is the resistivity, and R is the resistance in this equation. We can see thin film resistor structure and gallium arsenide based resistor structures. There are the structural difference, and also there are some activational difference between two types of resistor. Now we will discuss on transmission lines. Transmission lines and waveguides can be defined as devices used to guide energy from one point to another. That means from the source to the load. The transmission lines can consist of a set of conductors, dielectrics, and combinations. However, the transmission lines are almost always microstrip for MMIC purposes, although the coplanar waveguide transmission lines have been used as shown in Fig. In Fig, we can see a transmission lines, the microstrip, and the grounded coplanar waveguide picture. Here also substrate gallium arsenide in this figure. Couplers. In power division, an input signal is divided by the coupler into two or more signals. For lesser power, the couplers can be 3-port components with and without loss, and can be a 4-port component. The 3-port networks take the form of the T-junctions and other power drivers, while the 4-port networks take from the directional couplers and hybrids. We can see the pictures of different coupler and the branch line coupler, first one, and B figure the ring coupler. This one is the coupler line structure, this is the large coupler line structure, and this is the Wixon coupler structure. isolators and circulators. An isolator allows the microwave signal to pass in one direction but not in the other, which can be achieved by using ferrites. A ferrite material metal is mounted inside as the waveguide, and an external magnetic field supplied by the C-shaped permanent magnet. However, a circulator routes the microwave signals from one port to the device to another. For example, if a signal is placed at port A and port B is well matched, the signal will exit at port B with very little loss, typically 0.4 dB. If there is a mismatch at port B, the reflected signal from port B will be directed to C. Figure 1, the schematic diagram for mechanism of circulator for isolator for understanding the mechanism for isolators and circulators. Now I will discuss on via hole. The via holes are used in microelectronics to connect different metal layers in integrated circuit, but also can be used to electrically connect both sides of a silicon wafer. These so-called through wafer holes and via holes. Via holes are etched through the gallium arsenide substrate, usually from the backside of the substrate to minimize the topside element area. The etching may be accomplished using a wet and dry process, which is followed by a cold step, sputtering, and finally a gold plating step to fill the hole with gold. An ideal via hole in gallium arsenide substrate is the schematic diagram. Now we'll discuss another important topic, the metal ear bridge. The ear bridges and crossovers are required for most MMIC layouts. An ear bridge is simply a metallic bridge that permits two transmission lines to cross over each other without formation of an electrical short circuit. The ear bridge shown in Fig are fabricated by depositing a layer of material to form the bridge connections of ports. Then a second photoresist pattern is developed and defining the bridge. A gold layer is sputtered onto the wafer and the bridge interconnects. The metal is plated to the proper thickness. Its reliability depends on the bridge metal thickness, the contact or port size, and bridge height and interconnect metal used. And a schematic of the metal layer bridge in Fig 1.17. Here also gallium arsenide has used in substrate. The another point we'll discuss wire bonding and bond pairs. Interconnection is very important or crucial between MMICs and is accomplished by wire bonding. The bond pairs are provided to allow wire bonding for electrical connection. Additionally, through the wire bonding and the bond pairs, DC bias can be supplied and output signals can be taken out. However, in the process of the wire bonding, the serious consequence can arise due to the low pass characteristics as shown in figure. The figure for wire bondings, and there is a band port to connect different devices on the chips. There is a bond pad, and this is the regions for parasitic capacitance are created between the metal plate in this region. The use of interconnection in MMIC is required, we know, but another bonding technique is the flip chip bonding, and another technique, the flip chip method shown in Fig. This technique are used solder bumps, and solder bumps are used rather than the wire bond pairs or another matters. These bumps avoid and the low pass characteristics of the wire bonding connection. Thank you. That's all for my side today. Thank you all.